Assalamu alaikum. Today we want to talk about Chapter 9, Part 1, Molecular Geometries. Now we saw in Chapter 8 that Lewis structures help us understand the compositions of molecules and their covalent bonds. However, Lewis structures do not show one of the most important aspects of molecules, their overall shapes. So the shape and size of molecules, sometimes referred to as molecular architecture, are defined by the angles and distances between the nuclei and the component atoms. Now, one of our goals in this chapter is to develop a sense of the shapes of molecules and how those shapes are governed in large measure by the kinds of bonds that exist between the atoms making up the molecules. So our first goal is to learn the relationship between two-dimensional Lewis structures and three-dimensional molecular shapes. Armed with this knowledge, we can examine the nature of covalent bonds. Let's start with molecular shapes. In Chapter 8, we used Lewis structures to account for the formulas of covalent bonds. Lewis structures, however, do not indicate the shapes of molecules. They simply show the number and types of bonds. For example, the Lewis structure of CCl4 tells us only that 4 Cl atoms are bonded to a central carbon atom. Now, the Lewis structure is drawn with the atoms all in the same plane, as shown in Figure 9.1. However, the actual arrangement is the Cl atoms at the corners of a tetrahedron, a geometric object with 4 corners and 4 faces, each with equilateral triangle. So this is the tetrahedral shape of CCl4. Notice that all carbon Cl bond lengths are the same, 1.78 angstrom, and also all Cl carbon Cl angles are the same with the value of 109.5. So we begin our discussion of molecular shapes with molecules and ions that, like CCl4, have a single central atom bonded to 2 or more atoms of the same type. Such molecules have the general formula ABN, in which the central atom A is bonded to N B atoms. Both CO2 and H2O are AB2 molecules. For example, whereas SO3 and H3 are AB3 molecules, and so on. So the number of shapes possible for ABN molecules depends on the value of N. For example, an AB2 molecule must be either linear or bent, whereas an AB3 molecule, the two most common shapes place the B atoms at the corners of an equilateral triangle. Now, if the A atom lies in the same plane as the B atoms, the shape is trigonal planar. If the atom lies above the plane of the B atoms, the shape is trigonal bipyramidal. So, again, the shape of a molecule plays an important role in its reactivity. That's why we want to study this. Now, the shapes that, by noting the number of bonding and non-bonding electron pairs, we can easily predict the shape of the molecule. Now, the shapes that maximize the separation of outer atoms are shown here in this figure. In addition to the shapes we have already seen, this figure shows those encountered when there are 5 or 6 atoms surrounding a central atom. Then we have linear, AB2, AB3 trigonal planar, AB4 tetrahedral, AB5 trigonal bipyramidal, and AB6 octahedral. Now, the trigonal bipyramid can be thought of as two face-to-face trigonal pyramids, whereas the octahedron is like two face-to-face square pyramid. Now, some molecules have shapes other than those shown in this figure, but we can usually derive the shape of those molecules from figure 9.3. Neither trigonal, pyramidal, nor bent is shown in this figure, for instance, but in figure 9.4 shows how we can arrive at these shapes by removing atoms from the tetrahedral shape. Okay, now, why do many ABN molecules have shapes related to those shown in that figure, and can we predict these shapes? When A is a representative element, one from the S block or P block of the periodic table, we can answer these questions by using the so-called the valence shell electron pair repulsion model, or the so-called the Vesper model. Although the name is rather imposing, the model is quite simple. Let's begin talking about the Vesper model. What determines the shape of a molecule? Now, simply put, electron pairs, whether they are bonding or non-bonding, repel each other. You see here we have 3 bonding pairs and 1 non-bonding pair. By assuming the electron pairs are placed as far as possible from each other, we can predict the shape of the molecule. For example, the Lewis structure of NH3 has 4 electron domains around the central nitrogen atom, 3 bonding pairs represented as usual by short lines, and 1 non-bonding pair represented by dots, as you can see here. Electron domains. We can refer to the electron pairs as electron domains. Now, in a double or triple bond, all electrons shared between those 2 atoms are on the same side of the central atom. Therefore, they count as 1 electron domain. Take this, for example, this molecule, AB3. Does it obey the octet rule? No, because it has more than 8. Then how many electron domains it has? The central atom in this molecule A has 4 electron domains. 1, 2, 3, and this double bond is counted as 1 electron domain. Now, the Vesper model is based on the idea that electron domains are negatively charged and therefore repel each other. The best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. So, as we saw in the example for CCl4, the 4 chlorine atoms, they are far from each other, and this will minimize the repulsions among them, and this is the best position for them. Now, these arrangements, together with those of 5 and 6 electron domains, are summarized in this table 9.1. So, this is electron geometries as a function of number of electron domains. These are the electron domains geometry for 2 through 6. You see, 2 through 6 electron domains around a central atom. If the number of electron domain 2, then it's linear. The predicted bond angle is 180. 3, this is the arrangement of electron domains, trigonal planar 120. 4, tetrahedral 109.5. 5 here, we have, this is the shape, and we have trigonal bipyramidal, we have 2 angles. You see 120 here and 90 here. And then 6 domains octahedral, and the angle is 90. So we can generalize the steps we follow in using the Vesper model to predict the shapes of molecules or ions. Then, what is the first step? Draw Lewis structure, as we learned in chapter 8. Count the number of electron domains in the Lewis structure. Determine the electron domain geometry, which corresponds to the number of electron domains, and use the arrangement of the bonded atoms to determine the molecular geometry. Now, figure 9.6 shows how these steps are applied to predict the geometry of the NH3 molecule. So again, then draw Lewis structure, determine the electron domain geometry, and it's tetrahedral. Then use the arrangement of bonded atoms to determine the molecular geometry, which is called pyramidal, trigonal pyramidal. So the electron domain geometry is often not the shape of the molecule, however. Then again, use the arrangement of the bonded atoms to determine the molecular geometry. Molecular geometries. Now, within each electron domain, then there might be more than one molecular geometry. For example, here we have tetrahedral, AB4, AB3 with one non-bonding pair, trigonal pyramidal, AB2 with two non-bonding pairs, it's bent. Again, so within each electron domain, so the electron domain for all of these is tetrahedral. However, the shape is different. This is tetrahedral, this is trigonal pyramidal, and this is bent. Now, this table shows us electron domain and molecular geometries for 2, 3, and 4 electron domains around a central atom. Then, again, these geometries are important because they include all the shapes usually seen in molecules or ions that obey the octet rule. Then, number of electron domains 2, electron domain geometry, bonding domains, non-bonding domains, molecular geometry, and the example. So in the linear domain, there is only one molecular geometry, linear, linear, because we have two bonding domains and one non-bonding domain. Note, if there are only two atoms in the molecule will be linear no matter what the electron domain is. For example, NO, CO, etc. If the number of electron domains is 3, then there are two molecular geometries. Then electron domain 3 bonding and 0. Then this is called trigonal planar if all the electron domains are bonding. You see, example is BF3, and here it's bent if one of the domains is a non-bonding pair. Then we have bent like this ion called NO2 minus. Now there are 3 molecular geometries with if the number of electron domains is 4. Tetrahedral if all are bonding pairs, then tetrahedral. Then the trigonal pyramidal if one is a non-bonding pair, as you can see. The above example is CH4, this is NH3, and bent if there are two non-bonding pairs, two bonding and two non-bonding, then we have bent, as you see in the example of water. Now let's look at this sample exercise using the Vesper model that we have learned. Use the Vesper model to predict the molecular geometry of O3 and SnCl3-. So here the plan, then to predict the molecular geometries of these species, we first draw their Lewis structures and then count the number of electron domains, as we said, around the central atom. Now the number of electron domains gives the electron domain geometry. We then obtain the molecular geometry from the arrangement of the domains that are due to bonds. Then for O3, you remember we have two resonance structures. Because of resonance, the bonds between the central oxygen atom and the outer atoms are of equal length. In both resonance structures, the central oxygen atom is bonded to two outer oxygen atoms and has one non-bonding pair. Thus, there are 3 electron domains. Then, 1 ion, 1, 2, 3. Remember that the double bond is counted as a single bond, as a single electron domain. So we have 1, 2, 3 electron domains. Now the arrangement of 3 electron domains is called trigonal planar. Recall from table 9.1. Now 2 of the domains are from bonds and 1 is due to a non-bonding pair. So the molecule has a bent shape. with an ideal bond angle of 120. Now for the second example, this ion, the Lewis structure for this is this. Remember that we have 1, 2, 3, 4. We have 4 electron domains. So it is tetrahedral, but the molecular geometry is different because we have 3 bonding pairs and 1 lone pair. So the molecular geometry is therefore trigonal pyramidal, and this is from table 9.2, like that of NH3, as you can see here. We stop here. This is end of part 1.